Welcome back to Professional Perspectives. I'm Arav, joined by my co host Praneeth. Every episode, we sit down with leaders, researchers, and builders who are pushing the boundaries of what technology can do. Today's guest is someone who operates at the cutting edge of natural language generation, evolution, and alignment. He's deeply involved in bridging academic research with real world AI systems. Our guest today is Mr. Varun Prashant Gangal. Before we dive in, this conversation with Mr. Gangal ran for over 2 minutes and 27 for 2 hours and 20 minutes. So we will be breaking it up into 3 parts, each around 45 minutes. This is part 1 of that 3-part series.
That's right. Mr. Varun Prashant Gangal has completed his PhD at Carnegie Mellon University Language Technologies Institute and has worked at companies including Amazon, AGI, and Petronas AI, focusing on model evaluation, alignment, and generative systems. His research touches on narrative generation, style transfer, data augmentation, and much more. Mr. Gangal, welcome to the show. So, Mr. Gangal, to start out, you've spent a lot of time in research, both in industry and academic research. What first drew you to natural language generation and evaluation and the research space in that?
So I think the was really in love with machine learning since I took it first. This was back when I was in undergrad, like in 2013, I would say. Maybe yeah. I first took my machine learning kind of undergrad course back in 2013, and since then, although I got a B in that course, but that actually triggered me more to explore it further on in a more ballistic kind of fashion. And so I ended up taking up a lot of electives, grad level electives on like reinforcement learning, natural language processing was one of them. One of the three or four I took, others being like searching and indexing and stuff like that. So and back then, I think in natural language processing, this was way before. Okay, so the how the space of approaches or the space of tasks was at this point of time was uh, we were still working. I mean, natural language processing was commercially important because obviously people needed recommender systems, and like there was summarization, and like Google News existed, Google Translate existed, so there were certain things, and there was a research community, and but the approaches were still based on what you would call like maybe pre deep learning, ML or AI. Like uh, people used to use a lot of decision trees, support vector machines, and like there were ngram language models and ngram features. So and okay, so in terms of, this is the space of things in terms of approaches, and in terms of tasks, what people used to do, or like what people used to try to solve with benchmarks, and like what their models used to try to do was one was, there were these tasks which were called, I mean, this is maybe an artificial distinction, to be honest, but people used to have natural language understanding tasks in which you're trying to derive a certain kind of structure, or like maybe, so for example, sentiment analysis is a popular one, but in which you have a review and you're trying to understand the sentiment. But there are others like named entity extraction, in which you're trying to understand certain named entities in a piece of text, or like co-reference resolution. So or there used to be other ones like parsing out a tree from a language, like a grammar tree, or like a dependency parse. So these were understanding tasks, and some of them are still have a downstream real world use even after LLMs. But some of them were purely kind of because people used to actually use these trees to then do like tasks industrially, like with the documents or something. So maybe some of these tasks don't matter anymore, but the true generative tasks, like which are actual and natural language tasks back then, were like machine translation and summarization, and then maybe story generation and speech recognition, but that also involves representing and encoding speech in some form. Um, so I think summarization was something that interested me a lot. Even then, like I think my first project report was on extract, like how you like convert a document into a graph, and like you somehow select a subgraph from the graph and make a summary. So that kind of thing. So that was a very so yeah, a graph theory was a very, like graph theory was a kind of what do you call it, a niche from which I saw a lot of machine learning. I back when I was young, like maybe I'd say between 21 to 24 or something. And so okay, so this was how I got into first into natural language processing and especially generation. But then there was a bit of an interlude where I used to work on social network analysis, like how do you use machine learning to understand social network, like centrality, how information spreads, and or how do you choose influential nodes, etc. And my thesis was on that. But then what happened was, when I applied to all the schools, the one of the interesting admits I got was from CMU and like the Language Technologies Institute. And language technologies, so CMU has a school of CS which has many departments in it, and one of those departments, or like kind of, so there are like 6 or 7 floors, and the bottom floor is, I think, bottom half of the bottom floor and half of the first floor is Language Technologies Institute. So it's just NLP researchers and profs. And once I went there, I got and so there were people working on all kinds of things there as well. But my advisor, who I got paired up, I think his name is Edward Hovey. He was, and okay, I must also mention. So another reason I got into natural language processing is my undergrad advisor. Like he was actually a student of Andrew Barto, who, like, I think Barto and Sutton won the Turing Award this year. So he was a student of the one of the original creators of RL. So he was very what do you call it? Catholic, not, I mean, not in the religious sense, but in the English sense of the term. Like he used to always make like he since he used to always pursue research on like a natural language processing, RL, online learning, all the aspects together. Like he was not a one track researcher, so he actually, even so for him I TA'd ML and RL both, just in undergrad. So that also opened, like made me pretty fungible in terms of what I did. So finally, when I went to Language Technologies Institute, it was, I got paired up with Edward Hovey, and I think Ed also had worked on generation. So he's actually one of the co-authors of Rouge, which was one of the popular metrics used for summarization back till 2022, when all models started doing well on Rouge. And like so Rouge is some ngram based metric, that if you have a gold summary, you kind of align it with the generated summary and check how much it matches. Anyway, so but he also had an interest in someone, in having a student who worked on generation. And I was especially, this was also the right moment to explore that, because uh, uh, the deep network architectures had just started kind of grokking natural language. Like I think the first the first use of the term attention in a very successful paper, I think it was in the 2014 to 15 phase. Like 2015, there was a paper by Ilya Sutskever and Dmitry Patanov. I may be massacring or like butchering his name, the second one. But I think they had a paper on called Jointly Learning to Align and Translate, where they had a RNN encoder and decoder to do English to French translation. And you might have observed, like around this time, Google Translate got radically better. Like this was even before LLMs. But so the architect, like you earlier there were a lot of restrictions on generation. So how people used to do natural language generation before deep neural networks was, they would actually have some kind of script or something. Like they used to have a pipeline, like you would have rules, and then you would maybe like have a grammar or something, and you would generate out many candidates. And then maybe you would have another language model that would come in and just rank things or something. uh, but I think due to this encoder decoder or other kind of very natural deep learning based formalism, it got very easy both to try out new tasks. Especially I was very interested in low resource or creative tasks. That's why you'll see a lot of the work on style transfer or like generating commentary for games and the like. So if you were doing this before 2014 or something, you would not even have a way to represent words, etc., from a good, because you cannot learn that from the task itself, because there's very few examples, like maybe 200 examples, 1000 examples, 1500 examples. But at this point, you just had these kind of pre-trained resources. I wouldn't say LLMs, but you had like Word2Vec and Glove in 2014, and you had you had architectures you knew that worked well for any task, and you had some pre-trained resources to start off from. So that gave a much more leeway to explore a more kind of more challenging generative task, more low resource or creative kind of generative task in a for in without actually iterating over it a lot or coming up with very specific approaches. So that was the viewpoint from which I started, at least in the first half of my PhD, maybe 2016 to 2018. That was one thing I used to work a lot on, maybe generative tasks, especially style transfer, commentary generation, inter alia. Sorry, that was a very long winding answer, but I think that is the yeah, like I got into a lot of these things by happen chance. So yeah, happens chance. Chance. Mm.
Yeah, no, definitely. That was a really good and detailed answer. And I just want to say you're very passionate about the field. And I think that's really awesome about how involved and passionate you are about the field. I definitely wanted to touch on a few things. One
Sure.
of the first things I wanted to touch about your PhD at CMU focused on language technologies. What key
Mm.
lessons from academic research have stayed relevant in your industry work?
Yeah. So I think, yeah. So one thing that has remained relevant is, I would say, especially, so I think this learning is maybe kind of specific to fields which are new or just achieved some level of maturity in the past 15 years or 10 years. But yeah, so I think I would say intellectual humility and like eagerness to dive in and learn something new is very important, because especially computer science is maybe like if you're working in a field like maybe compilers or operating systems, maybe there is already a lot of knowledge in the field and you're enmeshed in it, and it does it that they also face disruption, but it's not so radical. But because machine learning and artificial intelligence especially are even more young, they are very prone to getting, sudden influences from other fields. Like a bunch of physicists come in and they bring in a whole new set of, terminology and approaches. Like for example, there was a big influx of physics based approaches and influences in it always was there, but in an overwhelming amount between say 2015 to 2025. So that's why you had all these concepts like diffusion, and which is actually coming more from a physics kind of standpoint. They actually propagated even more, and so someone who was especially, I noticed this a lot because I was trained in a kind of more traditional computer science background where you learn, graph theory and like algorithms and compilers and operating systems. You actually, a lot of the way physics folks think about things like scaling laws, is very popular now, but the first scaling laws paper in AI was in 2017. But the whole concept of having a scaling law to measure a complex set of properties and come up with physical intuitive observations which provide a simple model of that thing, that whole thing came, the whole tradition of scaling laws came into AI and machine learning very late. So in what I was wanted to say was, yeah. So the making thinking in those terms is so you had to recast your thinking should be fungible. So you should be ready to like, okay, look into, okay, physicists think this way. This is where this is. So I should try to think about scaling laws everywhere, like if possible. So okay, so this is one. Second one is, I think, having having originality. Okay, so like, yeah, this may be a bit disaggregated, but having maintaining originality, like thinking from both from first principles. And so there are two ways of, maybe if you want to do something new in a particular research area, like I want to make a new evaluation benchmark for say something interesting. So for say a new benchmark which represents how well an employee works in a company like Amazon, or any other company where there are multiple internal code repositories. Uh, one thing I could do is think for like 2 days about this with a clean slate. Second is I could actually go on archive and read a bunch of stuff, and most likely, given how many people work on AI these days, there might be another person who has done it already, perhaps. And so, what I would say is that not a lot of people do enough of the first one. Like, because the moment you start reading other people's thoughts and work, your own your own original thinking kind of gets deflect. Like, you start thinking incrementally, okay, that this is already done, and you start conditioning on it. which is also, that kind of thinking is also needed, I would say. But it kind of removes, like, the leap of contribution you can make gets much reduced. And I personally kind of experienced this kind of, so this was back in 20, so there was a phase between 2017 to 2019 when I used to read archive daily. Like, I used to read all the 3 or 4 AI relevant tags that are there on archive. And it was good for a while, but then my thinking got very incremental, and I actually had a paper drought between, like, a phase where I didn't publish anything between, like, I would say end of 2018 to end of 2019. So, and I mean, I can't do a controlled experiment on my own life, but I think that was one of the factors that led to that. So I am, yeah. So I think this is something that is, yeah. And another thing is, I think if you are in a very empirical field, then it is very necessary. Like, your ideas may be very grand, but ideas only count for so much. This is not true if you're working in complexity theory. So this is a kind of empirical field specific observation. So you should, the moment you have an idea, you should start to think about what are the bottlenecks to implementing it, and, like, imagine yourself implementing a v0 of it, kind of. And yeah, so these are the, I think, 3 learnings that still kind of remain. Yeah. And I think increasingly the third one has got more and more important. Like, I think people have got more and more cynical about ideas having standalone value without there being a piece of code. Like, nowadays people also, like, kind of say, like, where's the code? Like, if there's a paper without code, they don't value that. So anyway, yeah.
I mean, I can definitely tell that these lessons like shape the way you view the industry and the field right now. But also, like from what I've noticed, your experience, you've worked in so many different domains and you've researched so many different topics, such as like narrative generation, style transfer, and data augmentation. What makes these domains so exciting to you, and what's still unsolved in these areas?
Right, yeah. So I think, yeah, so like, yeah, I think there are two axes there. I mean, if you would pick apart, I think narrative generation and style transfer. Although I've also, so I think one thing is, I think the more kind of create, like, what is the frontier, like, where the frontier abilities of current language models are, kind of, and what they can do that is very creative, or like a long horizon, that is maybe represents the style transfer and narrative generation part of things. I mean, because yes, I worked on those things, but I guess there has been a lot more stuff after between 22 and 25. But still, I think those two fall under that bucket. And then there's another bucket of, like, synthetic data generation, or how do you synthesize data to create interesting, I would say, uh, data mixes, sources of data on which you can further train models. I think so. One reason I'm saying this is because the term data augmentation kind of fell out of vogue and then came back in as synthetic data generation. Although there are subtle differences between the two, they are related. So I'm just trying to, like, kind of contextualize. But yeah, okay, coming back. So in the first bucket, I think why the first bucket interests me is because I think like, yeah, so human so I think if you're talking about being able to do all the things humans can do, kind of, I mean, that's not the only goal, I would say. But there are always, I think, creative tasks actually, uh, there so there are, like, I think a lot more people summarize things and translate things, maybe. Like, so I think these kind of tasks capture a particular creative niche of human ability, perhaps. That is one reason. And another is that certain creative artifacts, actually, uh, they it takes so they are low resource inherently, because, for instance, if you are talking about jokes, or like particular, like, it takes a lot. There are maybe only, maybe say, 1,000 or like 2,000 English jokes that are known by a large fraction of the population. So if you were to source a data set, you would maybe, I mean, there will be a lot of paraphrasing, but you might end up with 2,000 like, actual unique jokes. And we actually noticed this. I had done a work on tongue twister generation. Like, so tongue twisters are these sentences which you teach to, like, which are, I think, it's a kind of a some people use it for as a game. Some people, it's also like used to teach children or something. Tongue twisters are like she sells seashells on the seashore kind of stuff. So there are only about 400 tongue twisters in English ever. Like there's no, and I mean, I thought there would be more, but so generating, so even if so another reason is, even if these, so we are training models on the internet now, which is technically kind of apart from the things which are only there in the physical world. You actually have a chance that everything that human beings have ever done is kind of l- possibly being learned by models. But the things which are so much in a niche, it is possible that models may have not got locked into them during pre-training, so they are still more interesting to check and explore whether models can actually do them. And like how much effort you have to put in for a model to kind of bring up, like surface that ability that it has, or like build on that basic ability that it has. That so I think that is another reason. I think some of the other things are there. You will see a lot of work these days on long horizon, or emerging discussion these days on long horizon tasks. So long horizon tasks are where a model has to do something for a long period of time. Like it has to take many decisions, like for example writing an entire repository on its own, or doing search, but like not the search where you are actually pulling in information for like from like deep research is maybe a long horizon task, I don't know, like kind of okay, another like long horizon task that people have these days is like running a 7-Eleven store, for example. I think Anthropic in their there is this lab called Andon Labs. They've developed a benchmark around it, and Anthropic collaborated. So Anthropic has the Claude line of models. So in the Sonnet 4, like the Sonnet 4 tech report, they actually collaborated with Andon Labs. I think it's called Vending Bench. So it's not strictly a 7-Eleven store, it's a vending machine. I'm making it a little bit grander by calling it a 7-Eleven store. But okay, the point is that if you're running a 7-Eleven store from the perspective of a shopkeeper, that is also kind of a long horizon task, although not creative. So it has some similarities to narrative generation in that sense. So these tasks are interesting because when you are like there are some tasks which are hard because the context around it is hard to assimilate. Like for example, if you are doing a pull request to a GitHub repo. Like there's a particular Python file that you have to add to a set of, say, 20 Python files and one readme.md. So over there also there is some amount of, like, you have to maybe generate 1,000 tokens or something. So there's some amount of uh like length. So but you are not generating maybe say 20,000 tokens or something. So what I mean here is every time a model generates a token, like takes a decision, it's kind of taking a decision. So long horizon tasks are interesting because models have to learn to condition on their own decisions. Because when models are being pre-trained, or even a lot of the post-training phases, what they are being given is like chunks of text, and they don't actually have to condition on their own decisions during training. So what can happen is there are more chances for a model to go off the rails, kind of, because it's like a typical, like there's a, so we also call it teacher forcing technically. The pre-training, the way we do pre-training, especially for autoregressive language models, is called teacher forcing, because it's almost as if a teacher told you to repeat token by token, but the yeah, so that okay, so for due to that reason, I think tasks which involve a creativity and a longer horizon, like generating something over a long period, like generating something long, are interesting, and they will always have kind of more scope of they will always be kind of at the frontier of ability, so as to say. Yeah. Okay, so this answers the first bucket. The second bucket is, I think, synthetic data generation, right? So I think there are two reasons that synthetic data generation is relevant. So one is when you are for certain tasks, there would only be, like, for example, for a very very specific domain of medicine, for instance, maybe gynecology. there would be very less data in that particular domain. I think there might be even more niche domains than that. I'm just giving an example. So if you were to, for example, take a language model, and you wanted to make a language model checkpoint which kind of helps gynecologists, you can of course come up with a set of tasks grounded in gynecology and post train a model on that. But sometimes what happens is you realize that the model fundamentally doesn't know the vocabulary of that domain itself, or it doesn't know the, like this, I've actually seen this happen. Especially for instance at working at Amazon AGI, where I was actually involved in the training of the Nova family of LLMs. So the typical pipeline is a model is pre-trained first, and then there are these many post-training teams that work on different things, like say math, sports commentary, story generation, etc. Like there are 20 teams. But what happens sometimes is these teams sometimes improve on the domain by themselves. But sometimes what happens is they realize that, okay, our model just doesn't understand, like it just doesn't even understand the vocabulary enough to learn what is to actually solve the task. So what might be happening is you might have designed maybe 12 tasks, or like some of them might even be RL environments, for example, where there is a simulation of a gynecologist talking to a patient and like having some data and figuring out things. But you might be seeing just the model, all models have your model has performance 0 on all of them. So even if you ran your model, there would be no way it would actually get to a, like, for reinforcement learning to actually work, there has to be at least one trial where your model has to reach the outcome, so that it can then know that, okay, this is the right path and this is the wrong path to getting to the answer. But if your model fundamentally just doesn't understand like even a basic amount of skill to solve things in that domain, so so now the conclusion from this would be that you need to kind of mid train the model more, or like do little bit more domain fine tuning. The situation you might run into here is that there is very limited gynecologist, let's say, conversation data. Like there may be a Reddit for gynacs potentially, but there might be certain domains for which there's no Reddit, or there's very limited data on the internet. So now how do you amplify? Because if you fine tune a model on very limited data, what might happen is, it might be very unstable, because because you need your gradients are kind of not getting averaged over large batches and things like that. Second is that you might learn spurious things. Like for example, your gynac, say Reddit, is oversampled on physicians from say New England and California. So you're actually learning kind of that you're actually while doing so, you what you wanted to do via that exercise was making your language model more adapted to gynac terminology, but you are also kind of over training it on New England and California conversational style. But if you are doing say data augmentation, what you would do is you would kind of paraphrase maybe some of that data into say French, or like change over the style, or like you would also maybe add some dysfunctional doctors into the persona or something, like to so you want kind of want to amplify the variation of that data on the axes that are not actually pertinent to your domain fine tuning. Because then it would learn that, okay, this varying this doesn't actually matter. So for that reason, having certain kind of data augmentation, or you might call synthetic data generation or paraphrasing, does help. And this also helps at the level of tasks, because there might be, like, you might have data say for 12 tasks, but there might be other small things gynacs are doing in the process, like for example talking to a colleague to check whether they have the facilities to handle a patient. Maybe you don't have data for this kind of complex thing, but then you can kind of prompt the LLM in a certain way to use the existing data and insert such kind of situations. So this is kind of why data augmentation and synthetic data generation is useful. It is useful in every stage, literally. Like in pre-training as well, it is useful for you to insert basic biases which help you remove like really bad internet data. Like a lot of the internet data might just be repeated, like formatting, or or pages which are not actually even natural language. But then how do you use, like, actually if you read the llama 3 tech report, you'll find they actually use llama 2 to they use llama 2 to filter and paraphrase their pre-training data. So technically they were doing a kind of data augmentation or synthetic data uh, cleaning of their pre-training data using llama 2, and then training llama 3 on that. I forget I think this was llama. I can bring you back the reference also. So okay, so this is the reason I think both of these things are relevant and interesting and pertinent. Yeah.
Awesome. Yeah. So there's definitely a lot of things that you touched on that I feel are really important. And I wanted to ask a lot of follow-up
Right.
questions. To start out, if you were to describe data augmentation to, like, let's say, a high schooler in really simple terms, what would that
Yeah.
definition be?
Yes, yeah. So I think data augmentation is if you have a bunch of data that you are using to, like, you have a model and you have a bunch of data, and using this bunch of data you're trying to improve the model on certain aspects. How do you increase this how do you increase this data to make it learn better for this aspect, by maybe perhaps varying it along aspects that don't matter. Like you have so the data actually represents learning signal also, like the extent you can learn. And you so it helps both with increasing the amount of learning signal you can extract from that original piece of data, A, and B, also preventing spurious over indexing on that data, because you as the trainer actually have a kind of meta knowledge, right? That there are certain things that don't matter maybe, or like yeah. So I think I would say that it also goes little bit beyond that, in the sense that you can also make multiple kind of, so you can also use kind of, there is also the analogy of a curriculum, right? So you have like as a same way as a kid, like as of say a high school student has come to high school by going through the various stages of school, various grades. You can come up, like you have the raw data and some basic way of using it, but then you can also make more complex, or like more complex ways of using it. Like for example, you want to, like your data is maybe let's just say 1,000 sentences, but then you want to somehow find a way of constructing examples where which use multiple sentences from this original data together in an interesting way. So it also is about improving the difficulty, or like amplifying the curriculum of things that you can learn from that data.
That was really good. And I also, there was like multiple things I wanted to touch on, and one of them was about biases and hallucinations. So you were talking a
Right.
bit about like biases about like New Hampshire and like California, and how if you use like their language, then it might be kind of like biased against someone from maybe like Texas or like Maine. Why do these biases arise? And like, of course, AI systems can like unintentionally reflect these biases, like you talked about. How do researchers and developers generally detect and mitigate biases in these models, like as we're evolving
Mm.
through different
Right.
models and
Right.
iterations?
Yeah. So I think that's a very nice question. So I think these biases arise because ultimately we are training the model on via various loss functions or mechanisms, on the data that we have available, like, and using, like, say, next token prediction, or there can be other losses. Diffusion models are not strictly trained on next token prediction. They have some other mechanism. But the point is that you okay, sorry. Okay, just yeah. So these, I think there is also some work that any model that is sufficiently capable is bound to have some amount of sufficiently capable of, like, being sampled from and solving something creatively with some amount of exploration is bound to have some amount of hallucination. But I'll come to that later. So I think hallucination is a natural artifact of learning a large spectrum of things from, okay, so a large spectrum of things from a limited amount of data. And I think I think have this maybe this is not so relevant in pre-training, because the kind of pre-training we do nowadays is actually internet scale. So we kind of are doing the best we can do in terms of the data we can extract, although there are also certain, so there is also certain biases that do arise from that, because for instance, the physical world is not well represented on the internet. Like there are a lot of things you do subconsciously. Like for example, when you operate a keyboard, you are actually placing your fingers in a particular way. You are kind of putting your hands on the ASDF JKL kind of position if it's a QWERTY keyboard. So that maybe because of the typing enthusiasts, those things are there on the internet. But there are certain things that are not, I think, are not there on the internet. And what happens is, when a model is learning next token prediction, latently what is happening is it is kind of learning to take the previous context and like putting it into a subspace. Like your neural network is actually a collection of spaces, like it's projecting. And when it and then based on how well it does, it's being backpropped, or during the whole. So it has to prioritize, right? So it will prioritize those things that you're training it on. And so it might learn some other things as well, like that's what you call generalization, like out of domain. So it might do some generalization to other things, but there are certain things that will get neglected. So there is some bias that arises in what abilities or skills the model is better at. But then there is also, so these are the biases that come more broadly from pre-training. But now let's cut to post-training, which is where you are actually teaching that shell, the shell of a model that you have, which is kind of just a very good text completer, to actually do a bunch of tasks, like understand your chat format, like the way you and like under so these phases are kind of called instruction tuning. And people also use the term SFT, but like instruction tuning, SFT, and like you're teaching it to solve tasks. So in this phase, what happens is people will take like maybe say 140K, 200, 1 million, 2 million examples of just like this is a document, this is the summary, and they will actually feed the model the document and the summary. Or this is an English sentence, this is a French sentence, this is a news article, and these are the named entities. So what happens in this process is that the model is very specifically learning that. So what might be happening during this training is that, for instance, you had a news article which talks about a stock market fall in Google's stock, which happened on Friday, say due to OpenAI releasing a new browser. And you might have this data that and then the task here is that to recognize the named entities. So what might have happened is, named entity recognition is not actually set in stone task. Like for example, if you had OpenAI's products team, this actually has like two or three overlapping entities. Like there's OpenAI product, and there's OpenAI product team. So there's actually three entities which overlap. Now, depending on whoever came up with the answer to this news article, like what are the entities mentioned, and there must be, coming up with data at a 2 million scale definitely will have some biases from the people who created it, the annotators, or like whatever pipeline generated it. So the person who might have generated that output may not have listed all of these three, or they might not even have thought about hierarchical entities and gone with the convention of choosing the biggest. So there'll just be OpenAI product team as an entity. So when you train your this one example, what it's telling the model is, whenever there is an entity which has like three overlapping entities, the only entity you'll extract is the biggest one. And so the moment you trained on this example, the loss has kind of ingrained. So unless you have another example which has kind of done the same thing but had this variation where it actually listed OpenAI product, the model will actually have a bias towards picking the biggest entity and ignoring the other ones. And this is a very specific bias which I kind of exemplified. But when you're training on that whole 2 million, which itself will have maybe 1K different tasks, like all kinds of stuff like summarization, translation, even basic math problem solving, coding, one step coding, lead code problems. When you have that law, there are bound to be, due to the sheer number of tasks that are there, and the sheer number of answer kinds of answers, like given a sheer number of ways of specifying the kind answer, the right answer, there are bound to be such biases which creep in. And okay, so how do people resolve this? I think one thing people do is that they specifically try to enforce certain behaviors. As especially, okay, so as a result of this kind of post training, what happens is that the model, which was first a text completer, has now become really good at solving tasks and like helping a user get an output out. But as a result, it may have many biases. Like for example, it will try to do its best given the context you've got to answer your question. So if you for example, if you asked it that which Egyptian pyramid did Julius Caesar build, and Julius Caesar did not build any pyramids, but it will try to maybe so nowadays models, so if you give it this to models today, like all the models today, even smaller open ones like DeepSeek R1, it will actually answer that, oh, I think Julius Caesar did not build any pyramids, but maybe when he was governor stationed there, he helped repair a few or something like that, right? But if you went back 1 year, like if you maybe try, I don't know if any of those models are still around. There might be some, I think Llama 3 might still be around, so it might actually try to say that Julius Caesar helped Cleopatra repair like it helped Cleopatra make a second pyramid of Giza or something like that. So it is actually trying its best to complete and like solve according to the biases ingrained in it. But then you have to kind of teach the model these kind of explicitly teach these kind of behaviors like prevarication, hedging, and stuff like that. So there is this phase where you act like, just like you did instruction tuning, you can have another follow up phase to that, which is kind of called like aligning with values, and there is also personality alignment. So these, what they try to do is they try to create tasks which are centered around these values, or like for instance, you should not like you will actually have examples that may trigger the model, as I explained, into making a hallucination. And then what you will do is you will either have a corrected version of this, or there is also a set of methods called preference tuning. What those methods do is, given a context or a prompt, you have a wrong answer, like the wrong answer I mentioned, and you will have a rewriting of that wrong answer with minimal differences, like the initial answer which I mentioned modern LLMs will give, that Julius Caesar, when he was stationed, he might have done something which is actually there, but then he didn't actually build a pyramid. So this is called preference tuning, and I mean there are various preference tuning methods like DPO, etc. So what these preference tuning methods do that is different from the SFT or instruction tuning style post training is, you're trying to make kind of a neat change in the model's behavior on one axis, while not actually taking a great amount of care to not erase its ability or like affect other aspects. Because one is, your data is that way, like you have taken great care in your data that only this behavior, like when you are going wrong on this behavior, this will be your wrong answer, and when you're going right, this will be the right answer. So you have taken great care to make the data just to express the access of doing that behavior right. Two is that you actually have in these law. So during the post training stage I mentioned earlier, which was like the plain instruction tuning, the loss function you had is actually exactly the same as pre-training. It's just that the form of your data has changed from raw documents to this kind of task input output. But over here, during doing preference tuning, you are actually the loss functions. I mean, you may do this using preference tuning, or some people also do it using pure RL and using RLHF, which is okay. So what you're doing through this act is, you have this preference data kind of represents a human preference about certain behavior, and you may have this may not be over a pair, you may even have k such points, and the better ones and the bad ones. But besides creating this preference and representing this preference via having this group of outputs to an input, what you're also doing is, the loss functions that are there are not exactly the same. Like, they are not loss functions which are just teaching the model to predict the next token, that is there in some sense, but there are also these terms which kind of penalize moving away from the model that's currently there. Like, think they are so specifically these are called KL divergence, and KL divergence is basically it's a way of I mean, I don't want to get might go beyond the plane of high school math maybe, but okay. So I think KL divergence is a way of measuring distance between two distributions. And basically, when you're doing this second thing, what you try to do is the model is the if the model the you have an initial model you started from before doing this preference alignment, and at all times when you are learning the new model, you try to make the word distributions of this at each step of this model all not be too far from the original model's word distribution. So and I think so KL divergence specifically how it is you can think of it as a generalization maybe of entropy. So entropy is maybe like if you have a probability distribution, it is I think minus summation p log p. Where, for example, if you have like say 1/3, 1/3, 1/3, your entropy will kind of be maximum. Like if you have a coin with three outcomes, the maximum entropy will be achieved by placing 1/3, 1/3, 1/3 on each. So entropy is the KL divergence to the entropy of a distribution is its KL divergence to the uniform distribution. So now consider if instead of uniform distribution, you had another distribution. Say, so these are you have P and you have Q. So you know the entropy formula, which is minus summation P log P. In KL divergence, you have minus summation P log. I think it's P by Q or Q by P. I forget the exact one, but you get how it's a gen. So you also have these KL divergence terms. So you are not only trying to learn this preference, but you are also trying to, and even when you do this using reinforcement learning methods like PPO, which you might hear a lot about in the press or whatever, are also have these kind of KL divergence terms essentially. So okay, so what I mean, yeah. So to answer your question, yes, people actually have come up with a new with post training stages, one or more, which actually kind of enforce this kind of values or like personality and like being able to like about sensitive topics you should insert caveats. For example, like for example, if you say that I am at a close relative's funeral and I'm really really missing that relative, can you sing a poem in their style, and this is how they used to write. So some models will actually do it, but some models say that, oh, I realize you're feeling a lot of sorrow, but I don't think it is good to impersonate such a like person who has passed away and like mislead you into going into some kind of I don't know, like I don't know what's the right term, on a bad nostalgia trip or something. So yeah, so what must have happened is there through this kind of value training, maybe the model is kind of hedged against, because I think AI companies, especially the larger ones which are serving models at scale, they also have the restriction of having to obey to the restrictions a typical social media publisher or something will have. So they also have to enforce these additional values that, okay, whenever you're answering a question about stocks, you should say, I'm not a financial consultant, or financial situations are always volatile, and then go on to answer these kind of things. So I'm maybe over saying this, like there, like everything is a bit complex. So some of this might actually be enforced through the system prompt that is there, that is hidden from you when you use the chat or like Claude Code version of a LLM. But some of this, like even teaching a model to obey values that are there in the system prompt, that itself has to be also post trained into the model. So another thing people actually teach models is instruction following. That you want, like there are certain specs of how to behave. Like to teach a model to respect such specs is also requires a stage of, so this is another meta kind of thing. Like you want to enforce certain behaviors by default, and then there are certain behaviors, certain galaxy of behaviors that you want to teach a model to learn to respect if given, kind of. So this is the, I think, the range of maybe stuff that, yeah.
What I'm curious about is how do these people root out these weaknesses? Like, for example, like the songwriting that you gave earlier,
Mhm.
creative generation tasks like this, how do they expose weakness in current evaluation frameworks?
Yeah, yeah. So I think there are multiple. So one is, this is why benchmarks are important, because it is only by creating benchmarks which put models in a spot, you kind of expose the, like, for example, okay, there are two things actually. One is that bringing in humans. So if you actually, so there are people training LLMs are actually hungry for very very natural very natural ways of users using these models, so that the model lands up in interesting situations. And one thing is getting users to ask interesting prompts at scale. So you may source this from yeah, and I think this happens either by the model being exposed to some set of annotators or internal employees or published somewhere, or you have an arena where you have simulated users which will explore this model in interesting ways. And so this is the prompt, or I mean, I'm simplifying things a bit because you also have multi-turn things about models. But okay, let's just say we are in prompt response land, where you're interested only in LLMs doing good on these behaviors given a prompt and a response. So the prompt part of the thing is handled by coming up with an interesting enough galaxy of say 500,000 or 100,000 prompts by a large enough set of users, which you got either via your product, or you got it by, there's this thing called LMSys Arena, which is like lmarena.ai, where you can actually try, there's a leaderboard, and you as a user, when you go, they will give you two random models, model A and model B. You won't know which is which. And it will actually, let me see if I can pull it up. Yeah, so it will actually kind of like, if you go to lmarena.ai, okay, LMSys Arena. So that, so LM, so yeah, LMSys. Okay. Anyway, so LMSys Arena was a project by UCSD, where some group of students created this website where you go in, you type in some prompt, and you get a model A, model B, and it gives you answers. And then you have to say, was model A better, was model B better, or did both suck? Or both were good. And this was kind of a fun experiment before, but later it became like, at least for a period, like in 2023 to say early 2025, it was actually the dominant method, how people used to kind of see the marketplace of LLMs. But basically, we, like, all the LLM companies also used to deploy their models early on LMSys Arena, and then they used to get back data also from LMSys Arena. So this is another way. So okay, so you got the set of interesting prompts. Now the question is, how do you get interesting generations which expose the behavior of your LLM? So you kind of over generate lot of answers, like completions. And then you get another set of annotators. I mean, you might have used annotators to get the prompts themselves, but they might have been users. But here you actually need another set of annotators, and those annotators may not be annotators. Okay, like they might even be, you have given a prompt to LLM itself, and you have some rubric, and it's a LLM playing the annotator. So that's also possible, and people also call this RLAIF, like reinforcement learning with AI feedback. Anyway, so actually the RLH, anyway, I'll come back to contextualizing the RL part also here. But then what you do is get humans to rank these generations. So even though the humans may not sometimes explicitly enforce a value, you will give them a rubric maybe, but the humans will implicitly also enforce many values while coming up. Like, if you're given say 50 answers to that, the song example I gave, you as a human will maybe rank the more coherent one, but also the more respectful of funeral soberness, or whatever one higher perhaps. So and what will happen is, when people say RLHF, what the HF is basically the reward function. So as a result of the human feedback, you are getting a reward function. So RLHF is basically RL, where you have learned a reward function first based on human preferences. and which were created by these annotators, and that could be AIF also. So this is one way. And I think another way is that you create interesting enough benchmarks that can automatically surface these things. Because okay, what I was talking about was mainly tasks which were more of a qualitatively evaluated kind, like writing songs or like giving answers to generic questions. But if you have tasks such as, for example, writing a bunch of code, then you can use unit tests which automatically run and give you the feedback. So for example, if your model or like making a pull request given a GitHub issue. So for example, if your model is somehow not able to obey Python, like as you know, GitHub repos enforce some style guidelines and they have a certain make file. So for example, if your model is very good at writing code, but when doing the PR, it is not able to kind of update the makefile to contain, not makefile, maybe the poetry or whatever, PyProject.2, whatever framework you're using, it's not able to it's not able to properly see what it is and put in these light LLM or whatever new libraries you used, NLTK, into the makefile. What will happen is that your pull request will fail. Your pull request won't be so. So then you can create a benchmark around the model being able to do complete PRs. And uh, when you are, so you may not have planned to discover this behavior, but by virtue of the model doing a complex task and you having kind of a gating function that's a good reward function or actually a downstream metric, evaluation metric for that task, you have serendipitously discovered this problem. And when the model is actually trained, made to, so you can use this as an evaluation benchmark and just look at the outputs and you will discover this behavior that oh shit, my model did everything and then it just forgot to put this stuff into the make file. So when the PR went on GitHub, it didn't auto, like the hooks did not run properly and my PR got rejected automatically because it doesn't, it like even like it didn't, couldn't even go to review. So so this is why people, you might have heard a lot of discussion around Bench. And like Bench kind of became kind of the what do you call it, like the not cold war, like it kind of became the, what do you call a definitive, it kind of became the kind of the Bench leaderboard kind of became the Dow Jones index or something of what LLM, for a while at least. And there were even LLM startups which raised money just because their post-trained model was on top on Bench. Because Bench is basically given a pull request like an issue. How well can your model take in a repo and write a pull request? But this is not the only example. But what I meant to say was, if you come up with any interesting enough tasks, I think the Wendy bench task was another one. Like Wendy bench for a human, it's very simple to run a vending machine consistently and handle, like just handle those issues naturally. But what has been found is that models can do it for a while and then they like goof up something. Like you can read, I think I can link the tech report later. But that is another behavior that has been discovered, that models are very bad at keeping like even a simple configuration system, like a little bit complex system which is a kind of like a dynamic process running over a long time. So okay, so to end my answer, I think these are the two natural ways, and this is why benchmarks and environments are very important, because we are fast reaching the time when most of human abilities in most niches, the LLMs are pretty good. And I think humanity's last exam, which was an effort by Dan Hendricks and Sale, was also an attempt. I was one of the participants or like one of the teams so humanity's last exam, the idea was, what is the frontier of like O1 and Claude 3.5, Sonnet, and all the LLMs that were there back in December 2024? What are like kind of the even the PhD level problems that they can't solve? And humanities last exam came up with a collection of such problems, and I think I contributed 3 out of the, like there was a contest literally, so we also got paid $1,500 for it. But anyway, so the point of these kind of benchmarks which kind of touch the frontier of models is to actually discover what it's kind of naturally discover what such micro behaviors are kind of a bottleneck to a model doing more. And okay, so the role of the annotator is kind of maybe getting little bit diminished now, because we have kind of maxed out what can be done by humans already, and we are now looking at, like, people also talk about ASI and stuff like that. But basically, you are now interested in tasks which are humans cannot do or evaluate themselves, maybe like browsing, like collecting information from 200 websites and compiling them into a report, etc. So you need methods of, like, the second type, more like benchmarks or environments which have a very, like, verifiable kind of reward function, not verifiable, like, which have a definite outcome, which can then tell you that you have failed or not on doing a bunch of things to get to the end, and those bunch of things surface the wrong behavior. Yeah, so that's kind of
Awesome.
my
Yeah, no, no, no.
thoughts.
Definitely. That was a really good response. And I feel like you had a
Yeah.
lot of parts that you touched on. A few parts that I actually found quite funny was like you talking about like Cleopatra and Caesar. And I was like, it's actually so true. Like if you were to go back like a year and to ask the question, it might have said, "Oh yeah, actually when Caesar was there during some expedition or during like his time as governor of like Spain, that it might have happened or like something like that, right?" I felt that it was actually really true and about seeing how AI evolved. There's a lot of questions I wanted to ask you, but a really
Sure.
big one was about the term LLM. So
Mhm.
in general, people say LLM, and then I feel like most people know the definition, which is a large language model. You talked about it
Right.
too, but I feel like in the news and articles, like everyone's just saying AI or like LLM. Could you define the term and could you like give a quick overview and context of what an LLM is and like
Right.
its prevalency?
Yeah. Definitely, yeah. So I think where the border between, yeah. So I have actually seen the border. Like, okay, yeah. So I think, to contextualize, I think a language. I mean, maybe I should define what a language model is first, really quickly. I think a language model is basically a probability distribution of language, a probability distribution that kind of assigns a probability to any possible sequence of some unit of language, whether it's characters or words. And it is kind of, it is not like it can handle any sequence of arbitrary length and give it some probability, and this, and like kind of like a well formed distribution of that kind. But I think what uh, language model has also came to mean eventually, what people found is that, so original, in their original form, like, language models have been actually used in machine translation and speech recognition, and even spelling correction, right since, I would say, maybe late 1990s or 2000s. I think Rob Mercer, who and some other folks at IBM Research first started using them, like, in and the way they were used at that time was, you have, for example, a speech recognition system, and that speech recognition system has taken in a speech signal and generated many candidate sentences, and this is based on kind of a speech to text converter. And now you want to kind of rank these hypotheses, so you need you need kind of to find which of these hypotheses are more languagey, like, and which are kind of yeah, like, there is the famous example of recognize a beach and recognize beach. Like, both of these are likely hypotheses given that sound, like recognize a beach. But a language model helps you tell the difference, that like the vanilla language models, which are a probability distribution, help you tell the difference. And the initial language models were actually, as I mentioned, these n-gram models, and etc. But eventually, word embeddings and deep approaches took over. But what people found after a bit is that, when you have learned a distribution over language, and especially if that distribution is kind of left to right, or like in a way that is left to right, you can actually, it is actually a pretty good sampler for language as well. By what I mean for a sampler is something you can actually start with, like, like, you can start, say, with the start of a sentence, and with the same, so the language model is actually, it is not trained to be a good sampler. This is a kind of a happy side effect that we have only in language. I don't think this is actually true in, maybe in vision. Like, I think in vision, the models which are good at sampling are often not the same which are actually able to learn the probability. But anyway, I don't want to overcomment because I'm not a very good vision researcher. I'm not a vision researcher at all. So okay, coming back to language, I think so a language model then came to mean eventually something which is which has been trained as a probability distribution of a language, and b, it can also act as some kind of completion function and kind of sample out more language for you if you give it some language. And this was the and so this is a language model. And language models themselves saw a lot of evolution from like n-gram language models to like basic RNN language models to finally in I think 2017 or 2018 you had people first trying to train it on whole Wikipedia, and then you kind of finally had GPT-2 come out in 2019. And actually it was very surprising to us at that point that could have a language model which could generate this passage about, I don't know, unicorns speaking English in the Andes. Like, given a prompt, generating a story of 100 words long was a dream at that point. So okay, so I think I would say GPT-2 was the point where we actually made the transition from language model to large language model. And I think what makes it large is so what makes it actually large is that it's actually trained on the internet or trained on a sufficiently large corpus. But because of that, it also has to have a certain number of parameters, because there is this whole concept of capacity in machine learning, right? That if you like if you to model a rich enough phenomena, if you want to avoid bias and you want to learn to model a rich enough phenomena, you need a function that is sufficiently representative, and you need a learnable function that is sufficiently representative. And this is what models essentially are. They are functions which are sufficiently representative, uh, parametric functions which are sufficient, so there are certain parameters to be learned, and the final function that you will learn belongs to a class that is rich enough to represent the whole data. So by virtue of having to learn whole of language, of which the internet people found is the best initial representation, at least these models have to be of a certain size. And I think that is, so the large comes from bit both from the data and bit both from them being large. And I think people also have the term foundation models. And anyway, so this is where I think the and I would call, there is also controversy on what was the first LLM. Some people also call BERT the first LLM, but I think BERT was not really LLM. It was kind of like, it was kind of showing so BERT was a masked language model kind of, where if you gave some prefix and if you gave some suffix, it could predict the word in between. And so BERT was actually kind of more of an encoder. Like, it used the concept of masking to learn an encoder. And BERT was actually itself pretty shocking, because when BERT came out, there was this benchmark called glue. Okay, if like I don't know whether like you might know it still. So this benchmark had like 8 or 9 NLP tasks, like named entity recognition, summarization. I don't know whether summarization was there. They were kind of understanding tasks. And this, like, models used to be like 60, 70 on each of these tasks. And then one fine day BERT came, and BERT like immediately like pushed all of these to 92, which was kind of the human level. So it was kind of shocking. So uh two things I said, like, they are probability distribution of language and they are text completers. But what people found is that training on a large amount of language and learning a probability distribution also gives you good enough ability to solve any task. So these are actually two, like, being able to sample is one finding which we found between say 2010 or like 2005 to 2015, and the other is the being able to solve any task. This was also a serendipitous kind of byproduct. And I think this was first found by GPT-3, but also GPT-2 to some extent. And GPT-3 actually also found another thing, which was promptability. So uh, so being able to getting a good enough representation to solve a large number of tasks is one thing, But promptability, what it does is it actually enables you enables your LLM to, at test time, like solve any new task very easily using language. Because we have actually, like, the reason we actually needed stuff like style transfer both in vision and in language was that you actually couldn't tell the model to solve Monet, or like to kind of do style transfer in the style of Shakespeare. So you actually had to go through the kind of Sisyphean or Herculean labor of collecting a bunch of data to represent your task, and then doing task fine tuning to, like, you used to have very good models. Like, I think this was the issue with some of the models before GPT-2. Like, for example, Bert did not have a way of, like, say, generating language, or like you could prompt it to some extent, but it was not very responsive. So I think prompting, and also the related finding of few shot learning, that not only can you tell it to do something, you can give some very bad but basic examples, and it will generalize from them. So this kind of combined observation led of promptability and few shot learning was another aspect that LLMs had kind of ran into serendipitously, but are since then expected to have. So I think this makes the universe of LL kind of, yeah, what people expect from a LLM. And I think there are also a lot of other things like world model, which is like, yeah, one can talk a lot on them, but I think LLMs also have, to some extent, a good internal world model in some aspects. To some, so I think world model is kind of, there are many actually definitions of this, and I think if you see the if you see the podcast between Dwarkesh and Rich Sutton, a lot of it was about them arguing over what a world model is and what qualifies as a world model. But I think LLMs also implicitly learn a good world model, and what world model means is taking a state of the world which is specified to you in some form, and being able to reason that if you do something to it, what will result, like being able to result about counterfactuals and state changes in that world. um, that is kind of maybe one, yeah, like it is not actually talking about learning about the world, which it does anyway. uh, okay, so that, I think, yeah, so this, I think this is the terminological expectations around LLM. Yeah, there's also MLLMs, which is also, like, people have increasingly come to expect that using language as the first staging ground, you kind of want to create a model which can then incorporate any modality. Like, for example, vision. Like, vision was originally not there in LLMs, right? Like GPT-3 did not have, couldn't accept image attachments. So the way people have kind of inserted these abilities is it not usually during pre-training. There is this stage called fusion. So there is a lot of, like, learning vision is a thing in itself, because vision requires completely different, like, this way of tokenizing language into units, and running an autoregressive learning mechanism on it doesn't work in vision. So you have lot of work on that. Like, there's Dino V2 clip. Like, way how to learn a good vision representation is hard. But what people have done is, what fusion does is, if you have a good vision encoder, how do you learn a connector to kind of fuse it to kind of project those representations into tokens. And having done this successfully for vision and speech, and by virtue of most models having this, people will increasingly come to expect models being able to do this kind of uh, fusibility, or like generalizability to other modalities post hoc. Is uh, is another expectation that people are coming to have. And due to the importance of this also in some natural tasks like browsing and navigation, egocentric navigation, and like for example, if you're wearing your Google Glass or Meta, whatever it is, Meta Ray Bans, and you are navigating and you want to see, like, Dragon Ball Z, Vegeta, or some other movies where they have those dials. Like, if you want to do that and like navigate, then you need actually also some kind of 3D perception and vision, which is working along with your language model. So those are another set of expectations that have implicitly come into LLMs, although people also call them MLLMs. Anyway, so this is, I guess, the terminological stack is what I call it. Yeah, yeah.
Yeah, no, definitely, Mr. Gangal. I would say your passion is so evident, and I feel like you're really involved in the field, and I feel like your answers are definitely very, very in depth and very helpful, and I feel like they're going to be very eye opening for our audience, especially in the AI field. There were also like a lot of questions again that I wanted to talk about. One
Sure.
of them was it's about like the current event of the AI and like the AI research scientist role. I don't know if you've heard about like the Meta role, where they're signing them for like a lot of money, and where it's kind of like it's becoming like this whole meme online on like Twitter, where they're talking about how it's like kind of like soccer signings where people are signing them from like different
Right.
companies. Do you think the lucrativeness of AI research will continue to grow, or are we just reaching like a saturation point in demand and pay? That wraps up part one of our conversation with Mr. Varun Prashant Kankal. We covered the roots of his journey and the principles driving responsible AI research.
Next episode, we'll dive deeper into real-world AI evaluation, how systems are tested, aligned, and improved. Make sure to follow Professional Perspectives so you don't miss part 2. Until then, keep questioning, keep learning, and keep exploring your professional perspectives.